Hi everybody, today we're looking at applications of antidifferentiation. So using antidifferentiation we can find a function from a rate of change and a range of values of x or a point on y. Okay, so what does that mean? Well, let's start with looking at what a derivative is. So on the top we're talking about what's changing, and on the bottom we're talking about with respect to what. So let's look at an example. Given a rectangular pool 2 by 3, that's the base, and 4 meters deep, that has a tap that's going into it with a flow rate of 5 liters per second, how deep is the water after 5 minutes? Now, we can do this really quickly without calculus, but we're going to do it using the calculus method, and then you can use that for more difficult examples later on. So here's what we start with. We start with some meter calculations here, some liter calculations here, some minutes here, and some seconds here. Now, as we know, we're trying to reduce this to two variables in the same units. So we have meters and liters. We can make it into centimeters cubed, this part, and centimeters cubed, the volume calculation will reduce itself to liters. So that's kind of handy. And we've got seconds here and minutes here. Well, 5 minutes is 300 seconds. So of the two things to work with, that's the easiest one to use. So we're going to start by looking at this volume problem. So volume equals 300 by 200 centimeters, which will give us 60,000 there, plus times by the height, however high it is. And if we had that in centimeters too, that would be h. Now, we can convert that later into liters, which would be kind of useful. So when we get to that, we'll have another look at it. Let's have a look over here now. Now we've got the rate of change. The rate of change is 5 liters per second. That's what's stated here, which would be 5,000 centimeters cubed per second. We should probably put the per second on the end of that. And we get that 5,000 centimeters cubed from 5 liters by knowing that 1,000 centimeters cubed is a liter, and we've got 5 of them. So that's nice and easy. Now, then we can say the volume equals 5,000 T plus C by antidifferentiating this function. So times the amount that we have by the time by however much we started with. Now, with this problem, we're going to assume that it was empty at the start, so C becomes 0, and we now have a formula for volume at any point in time. We know that we want the volume after 300 seconds because we worked that out from here. Multiply the 5,000 by 300 and you get, what's that, 1.5 million centimeters cubed. Now, we know that volume equals 60,000 H from up here when we're doing length by width by height. Now what we can do is rearrange the equation for height. Now, for some odd reason, I've dropped an H off here, so let's put that back on again. So I've said, look, this is the volume that we want. How high would the pool be? And if we divide those two figures by rearranging, we get 25 centimeters. So there we go. One little problem done. Let's have a look at a different problem. So this time we have a rectangular pool again, the same size, and it's normally filled to 3.75 meters, but 25 centimeters evaporated. So at 3 liters per second, how long will it take to fill the pool? So we can work out how full the pool was at 3.75, 22,500 liters, how much at 3.5, which was 3.75 take 25 centimeters, which is 21,000 liters. We can subtract that and find out that it's 15,000 liters divided by 3.5, and really trivially we can solve it without any calculus whatsoever. But let's do it with the calculus way. So we know at V0 it's 21,000 liters, that's here, and we want to know at how long will it take to reach 22,500. So do the same again. V equals 3.5 T plus C. That's the antiderivative of this function. substitute in the value that we know, 21,000 at 0 plus c, so that'll give us c equals 21,000, the startup value. There's our formula for volume. Solve for t when t is 22,500, the question that we posed up here, and we find out that t is 428.6 seconds or 7.14 minutes, which, like before, we could solve quite trivially as long as we understand what's going on. Let's have a look at another case. This one was probably not such a trivial solution, but a bit more difficult to understand. So we're going to produce a widget this time. The widget has a setup cost to produce it of $20,000 to produce one widget, and embedded in that is a cost of 200 times 100 divided by x plus 2 per unit produced. And we want to know how much will it cost to produce 100 widgets. So over here we have the cost per widget, which is what we were given here. Cost per widget, per x, per unit. 200 times 100 divided by x squared plus $2, which gives us this formula here. We can integrate that formula, we can anti-differentiate that formula. You'll hear me say integrate a lot because in the next course of work, we don't do a lot of anti-differentiation, we do a lot of integration. It's fundamentally the same process, but it comes from a different place. So once we get there, we'll start talking about it as integration, but for now, anti-differentiation is just the backward process from differentiation. Okay, so c equals negative 20,000 x to the negative 1 plus 2x plus c. We have anti-differentiated this function here. Now, we know that when it's produced 1 unit, it's $20,000, so we substitute 1 and 20,000 into the formula. We get c equals 3998, which gives us our cost formula. And once we have a cost formula, we can work out how much it costs to make 100 units by substituting in 100. And bang, there's the cost there. Now, we can look at how much should be charged per unit to make $200 worth of profit. So $200 of profit from 100 units. This is still bugging me. If the initial cost is, the initial cost is $20,000, so it does cost more. Good, okay. Yep, no, it's okay. So how much should we charge per unit to make a $200 profit from 100 units? Profit equals revenue minus cost. We want to make $200 of profit. We don't know the revenue, we do know the cost. Solve for revenue, and we get this. And if we divide then by the number of units that we want, so except I made a mistake up here. Well, I won't have to redo this whole thing again. Am I? No, maybe just this part here, because I want 100 units. And then that will give me the answer I expected. Okay, so that's not so bad. So solve for 100 and 200 gives us this amount. Divide by 100 gives us $401.98 per unit. Now, what if we produce 200 units? Is the cost per unit better? Well, let's check. 200 equals revenue for 200 units. That comes to this amount here. Divide that by the 200 units to get the price per unit, and we get $202.49. It's much cheaper per unit to produce than it is for just 100 units. That initial cost here is spread over more units. And you can get the cost per unit down. If you get the cost per unit down, you can get your charge rate down as well, your sell price. Okay, next one. A car is increasing velocity by 2 kilometers per hour for 20 hours in a straight line. If total displacement was 200 kilometers and the initial displacement is 0 kilometers, what was the initial velocity? Okay, so to know this, you would have to know that this calculation here, it's increasing its velocity by 2 kilometers per hour. So its acceleration is 2 kilometers per hour squared. The velocity is changing by this amount. So we can integrate that to get the velocity. We can anti-differentiate that to get the velocity. Here it is here. And we also know that the displacement over time is equal to the velocity. So if we anti-differentiate this, we'll get back to displacement. So I did that here. And notice that we've got two different constants now. And we've got the constant that we established for velocity, and we got another constant when we did our displacement. So its initial displacement was 0. There it is there. Sub 0 into here, and you will get d to be 0, which leaves us just with that part of the equation. We know that when it's after 20 hours, its displacement is 200 kilometers. So we sub that in, and we find that c equals -10, so v equals 2t take 10, and we can substitute 0 into that equation and get the initial velocity, which is -10 kilometers per hour, or 10 kilometers per hour going backwards. So it started going backwards, changed its direction, and went forwards after a while by continuing to increase its velocity by a little bit. So it went negative, 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 0, positive, positive, positive. These sorts of problems we get into a lot more next year. This is far more complicated than we have to do in year 11, but it's good for you to see it at this stage, because if you can get a good picture in your head, next year's work becomes quite simple. So I hope that was helpful, and I'll replace the one that I had up there that was full of errors, and hopefully this one has a few less errors. Thanks, guys.